So let's just begin then. So tomorrow is a holiday because it's 2nd October. So I will not record a. I will not upload a pre-recorded lecture. I'll see you again on in next week, Wednesday. But tomorrow there is one external lecture scheduled for geology of wells, and that deals with geomechanics, which is, although it's not very much included in the course for geophysics, but you know things are pretty much related. So if you are interested, you can please join tomorrow at uh, from 4 o'clock. So I already sent you the email invite. So if you can, please do join. Okay, let's begin. Where we stopped yesterday essentially was we were discussing about magnetic moments. And if we recap, magnetic moment is nothing but, in a very small dipole, it's the product between pole strength, and the distance between the poles, right? That's how we had defined magnetic moment. Now we said that if I look at any naturally occurring mineral, we can observe that it will have magnetic moments, of course, of different directions. So magnetic moment is a vector, so hence it will have the magnitude and an orientation, of course, oriented in many different directions. Right? Now, the size of the arrow represents its strength or magnitude, and the direction of the arrow represents its direction, right? So let us say it's fairly randomly oriented the way we have drawn it. So there is one term that I want to introduce here, what we call as magnetization. And magnetization is denoted with capital M. And magnetization is nothing but, if I essentially sum up all the magnetic moment in a particular mineral or a rock and divide that by volume. Okay, so magnetic moment per unit volume, it's a statistical average, is called magnetization. Okay. Now let us say that this particular material, and for our particular purposes, it is applied for all sorts of materials, but we will mostly consider minerals and rocks, right? So for example, this piece of rock which has certain magnetization, okay, certain that means there is certain orientation of its magnetic moments. Okay, I push it under some external magnetic field, and let us say the magnetic field can be directed in any direction, okay, any direction, and width of any strength. Let us say the external magnetic field is capital H. So what would happen when I subject this particular rock uh, under external magnetic field? This external magnetic field would try to align this magnetic moment along its direction. Okay, so what would happen? Say you know, some of them will be aligned more, some of them will be aligned less, but overall, it will try to align itself, will try to align the magnetic moments which are present in that mineral according to that age. Okay. So now how much magnetic moment will be aligned is defined by this particular formula. And that is a very famous formula that I want you to remember. M equals to KH. Okay, so M is essentially directly proportional to H. So that means if I have a stronger inducing magnetic field, okay, I will have more alignment. So that means my magnetization will increase. Okay. And the other thing that it is dependent on is this parameter K, which is constant for this particular material. So K is constant and which is essentially a function of the material. In this particular case, rock or mineral. And K is called magnetic susceptibility. Magnetic susceptibility. Now, if you look closely to K, okay, if I look closely to K, yeah, K is essentially a tensor. Yeah, K is essentially a tensor, and any tensor can be essentially represented by, an ellipsoid, okay, and it can be resolved in this ellipsoid as with the mutually perpendicular axis. Sorry, let me just draw it a bit bigger, okay? I can explain it better. So K can be resolved into, so it will have different components in all directions, but it can be expressed by an ellipse. And then, of course, the ellipse will have, three axes, of course. The major axis, the longest axis, we can call it as K1, and then the intermediate axis will be K2, and the smallest axis, let us call it as K3. Okay? And this is what we call as susceptibility ellipsoid. So what do I mean by that? That this susceptibility, this term K, is not essentially, is actually anisotropic. It depends on the direction. Okay. So the susceptibility along X direction is different with from its Y direction, from its Z direction. Okay. So if I take a rock essentially, because the magnetic moments are oriented in different directions, okay, the susceptibility value will be different in Z direction, different in X direction, different in Y direction. So that is what we call as susceptibility ellipsoid, and this magnetic susceptibility is essentially anisotropic. Now there is, of course, to simplify. So now if I say something has higher susceptibility, something has lower susceptibility, what that value we refer to, we call it as Km. Km. So in this K, where I have put M is equals to Kh is nothing actually is Km. It's the mean susceptibility, and mean susceptibility is nothing but K1 square plus K2 square plus K3 square. Okay, that's the mean of this three susceptibility ellipsoid. So A represents the susceptibility value. It is essentially dependent on the material. Okay, and this is anisotropic, can be expressed by an ellipse, K, which has three axes, of course, K1, K2, and K3. And then, we can actually calculate Km, which is the mean susceptibility. And mean susceptibility determines, how strong the magnetization will be of that material under a fixed magnetic field. Okay, so if you want to align these black vectors into these blue vectors, there are two things that you can do. One thing, of course, you can increase the external magnetic field, and the other thing, of course, you can change the material. If the material has higher susceptibility, that means it will be aligned more. Okay. Now, so depending on susceptibility, natural materials, natural material that includes rocks and minerals, can be broadly subdivided into three categories. Okay, and I'm sure you know about them. The first one is called diamagnetic. Second one is called paramagnetic. And then third one is called ferromagnetic. Okay? And ferromagnetic has certain, morphs, some morphs. Okay, we will discuss them in a moment. Okay, so now let us first start with diamagnetic material. So let us look at dia and paramagnetic material. Dia and para. Okay, I'll draw a graph which will explain both dia and paramagnetic material. Okay, so in the y-axis, I'm drawing M. M, that means magnetization. And in the x-axis, I'm drawing H, which is my external magnetic field. Okay, this is 0. So diamagnetic material is represented by a curve which looks something like this. So with increasing H, thus magnetization increases. Okay, the magnetization increases. Okay, but then, so suppose what do I mean by but thus magnetization happens in the opposite direction than that of H. Okay, or in the other words, we can write down K is negative, and this is what we call diamagnetic. So what do I mean by that? For example, here is now if I want to look at it from the magnetic moment perspective, okay, suppose this is my material and there are magnetic moments randomly oriented. Now I subject it to some external magnetic field, the capital H. Okay. Now, what this will do, this would essentially try to align them, but the alignment will happen opposite to the direction of H. Okay. There will be feeble alignment. The alignment will not be very strong. So the net magnetization will not be very strong. It's feebly magnetic, but the magnetization will happen, opposite to the direction of H. And such materials we call as diamagnetic. So the first thing is, of course, low susceptibility. Low susceptibility means the alignment will not be very effective, of course. And the second thing is, of course, negative susceptibility as well. So that is what defines diamagnetic material. Now, when we talk about different materials, whether it is diamagnetic, whether it is paramagnetic, whether it is ferromagnetic, there is one very important parameter that you have to always mention. Okay. So if I ask you, give me an example of a diamagnetic material, what is implied that I am asking that give me an example of a diamagnetic material at room temperature. Okay. Simply because if I elevate the temperature or if I actually decrease the temperature, okay, from the room temperature, its magnetic property might vary. It will not always vary, but in most cases, it actually varies. Okay, so a paramagnetic material can transform into a ferromagnetic material, and so on and so forth. I will show you one example of that, but then most of the minerals, most of the rocks actually behave in that way. Okay, so it's important to actually mention the temperature what you are referring to. If the temperature is not mentioned, then it means the way you find them in nature. That means room temperature. So, for example, one mineral which is at room temperature diamagnetic is quartz. Okay, one of the most famous quartz is in room temperature diamagnetic. Now, what is paramagnetic? Paramagnetic is very similar to diamagnetic. Only difference is K is positive. Okay, so if I try to draw it here, so these are my random digit oriented magnetic moments. And then I subject it to external magnetic field. Some of the magnetic moments will be realigned, Okay. Not all of them, simply because here also magnetization is not very high. It will be feebly magnetic. Okay, feebly magnetic. So the value of K is still low, but so K is low, but K is positive. Okay, that means the magnetic moments gets aligned along the direction of H. It's not opposite to the direction of H. Now you might ask me why such things actually happen. Why essentially in one case the magnetic moment uh, gets aligned opposite to the direction of H. In one case, it aligns itself according to the direction of H. Okay, and there comes your quantum mechanical explanation. It has to do with electron spin. Okay, and in one case, the electron actually spins in the same direction. In another case, it actually moves in the opposite direction, and that can be expressed by something called Larmor precision. I'm not getting into the details of it because it's not essentially relevant for what. I mean, it's relevant, but I mean, it's not essentially too much useful for the geophysical explanation. We are happy to know that there are some materials which are paramagnetic and some materials which are diamagnetic, and their basic definitions. And so, more important for us is actually prepare a list, okay, and that you have to do by yourself. Prepare a list of rock forming minerals, list of rock forming minerals, common rock forming minerals, okay, like the silicate minerals, oxide minerals, sulfide minerals, okay. So the ones that are, you don't have to find out for perovskite or fuchsite. These uncommon minerals are out of the list. I mean, nobody remembers them, but then you can always find them out from any textbook or for the uncommon minerals. But for the common minerals, yeah, For example, pyroxene, amphibole, quartz, olivine, magnetite, hematite, pyrite, sillimanite, pyrite, um, chalcopyrite, galena, the ones that you have done in your introduction to earth science laboratory, the common rock forming minerals. Okay, so prepare a list of the common rock forming minerals, yeah, with respect to their magnetic properties. That is essential for you. Okay, so which one at a room temperature is diamagnetic, which one is ferromagnetic, which one is you know paramagnetic. That is something you have to, it should be in your head. Okay. Now let us look at the paramagnetic mineral a bit more carefully. So for paramagnetic mineral, we have said that it is low susceptibility but positive susceptibility. Okay. Now, if I for paramagnetic mineral, if I draw susceptibility with absolute temperature, okay, I observe a relationship something like this, an hyperabolic curve. It becomes, sorry, or in other words, I can, like this. I'm drawing 1 by K. That is the temperature expressed in Kelvin scale or in absolute scale. So K to the power minus 1 is directly proportional to capital T. In some cases, you actually observe that the paramagnetic behavior actually starts after a threshold temperature theta. So after that temperature is crossed, okay, only then you will actually find the paramagnetic behavior to start. So in that case, k to the power minus 1 is directly proportional to E minus theta. So that theta must be crossed after that the paramagnetic behavior actually starts. Okay. And this particular temperature, and then so I can write down k is equals to c by t. C is a constant, of course, and that is the that is defined by the slope of this line. Okay, and this is what we call as Curie's law. Curie law. Okay, and this temperature theta is called paramagnetic Curie temperature. Don't be confused with the actual Curie temperature that we are going to discuss for ferromagnetic minerals. This theta or Tc, we call it as paramagnetic Curie temperature. Okay. So after that temperature, the paramagnetic behavior actually starts to take place. Now let us look at a typical ferromagnetic material. So, say for example, the clay group of minerals do belong to the paramagnetic minerals. Okay, the clay group of minerals are generally paramagnetic. Actually, all the minerals, some at some temperature interval, behaves as paramagnetic minerals. Okay, at some temperature interval, but at the room temperature, you will find that the clay minerals are generally paramagnetic. Okay. Now, of course, for ferromagnetism, what I observed that I have my you know randomly oriented randomly oriented magnetic moments. Then I put it to some external magnetic field. Okay. And what I will observe that, you know, if I put it for I keep on increasing the strength of H, and I will find that these magnetic moments will keep on aligning them with respect to H, along H, and there will be a time when most of them will be fairly aligned with the external magnetic field. Very so, and it will create very high magnetization on this particular material. So, if I just make the same plot, M versus H, okay, I find positive K and high K, because most of the magnetic moments are actually getting aligned with respect to H. Okay. Now, and this is something that you have all read before, the hysteresis experiment, the hysteresis loop. Okay, and what we essentially do, that is that I take a ferromagnetic material. Okay, then I subject it to external magnetic field, and we keep on increasing the intensity of external magnetic field. Okay? Keep on increasing the intensity of the introid somewhere else. So this is my material. So step by step, I keep on increasing the intensity of the external magnetic field. Okay, and then I watch its behavior. Okay, so H1, H2, H3, H4, H5, H5 being the strongest, and then I measured, of course, M1, M2, M3, M4. So while I'm increasing H1, while I'm increasing the strength of the external magnetic field, what is essentially happening, that all those magnetic moments, they are getting more and more aligned with capital H, right? So now if I plot diagram, and in the x-axis I draw capital H, and in the y-axis I draw M, which is magnetization. Yeah, what I observed that with increasing, so initially here H was 0, and then with increasing H, of course, my M keeps on increasing, and there will be a time when even if we increase capital H, the M is not being increased. Okay, so what does that mean? So that is the time when all my magnetic moments are optimally oriented. Okay, so I cannot orient them further. So that means it has reached to its maximum magnetization, or it is saturated with its magnetization. Okay, so now if I draw this curve, I can join these lines and draw this curve, and I can also attach an arrow associated with it. So that means, I'm increasing H, and M is being increased. Then it has reached a plateau, and this magnetization we call as saturation magnetization. Okay, MS, and MS stands for saturation magnetization. Now what I am doing, okay, let me just ask, because I have been talking for so long. Let me just ask: is the slide, I mean the whiteboard, visible to you, and am I audible? Everyone, can one of you confirm, please? Okay. Okay. And is everything clear so far? What I have talked about? Is everything clear? Okay. Because I have been talking and talking and talking, I just had to remind myself that sometimes it happens that the internet connection is lost. All right, so this is what we call as saturation magnetization. Okay, so once it reaches saturation magnetization, what I'm doing, I will reverse my magnetic field. Okay, so I'm now reversing my magnetic field. So if I reverse my magnetic field, what I will see, that the so now the next step is, of course, reversing magnetic field, and I am keeping on increasing in the reverse. So only the direction of H has changed now. I'm increasing. So what I will observe, that my magnetization will start to fall, but the magnetization will not start to fall in the same way. It will not follow the same curve. So it will follow a different curve. So now when I come to, because I have now reversed my magnetization, there will be a point when H will be 0. There will be no external magnetic field. Okay. But then what I will observe, even if my H is 0, okay, this will be cancelled out. Even if my H is 0, it will still retain some magnetization within it. Okay. So that means all the magnetic moments are not random anymore. So it has some permanent magnetization stored in the memory of the rock. Okay. And this is what we call as IRM. Let me just write this one down with red. This value is what we call as IRM, or MRS. We can also write MRS, the same thing, and that refers to isothermal remanent magnetization. Isothermal remanent magnetization. Okay. So if I keep on doing the same process, and then it will start to decrease, the magnetization will start to decrease. And then there will be one point at which, there will be one point at which the magnetization will come to 0. And then this value is called HC, or HC is equals to, called coercive force. Okay. Now, if I keep on doing the same thing, it will, reach saturation in the opposite direction. Okay. It will reach saturation in the opposite direction. Okay. And in most of the cases, this length, this height is more or less the same. And then if I again reverse, I mean, again, if I come back to the original steps, okay, it will keep on increasing the magnetization, but it will not take the same path. Okay? It will take a different path. And this is also called HC. This is also HC. It's similar. Now, if I essentially take this curve, and draw a mirror image of this one, we'll touch somewhere here, this curve, and make a mirror image at the other end. It will touch at this, and this value is called HCR, or HCR is called remanent coercivity. Okay. So from a hysteresis curve, there are 4 parameters that you essentially derive, and we will explain in the next class why they are important. So MS, that is the saturation magnetization, the MRS, the isothermal remanent magnetization or remanent magnetization, and then HC, which is the coercive force, and HCR, which is the remanent coercivity. Okay, these are the 4 parameters that you can generate from a hysteresis curve. So there is one particular instrument which is also present in our what is that called, central instrumentation facility in CIF. There is one instrument called VSM, vibrating, I forgot what stands for, vibrating magnetometer, right? I forgot what is actually stands for. Where this is one of the instruments. I mean, there are many other instruments by which you can generate such hysteresis curve. Okay, so there is one such instrument, that is what we have, which is called VSM, where you can actually generate such hysteresis curve. And the main parameters that you take out from a hysteresis curve are MS, MRS, HC, and HCR, and they are very much dependent on the material. Okay, the material. Okay, and we will see how MS, MRS, HC, and HCR, we can use them for our rock magnetic studies later on. Okay. We'll see that later on. Now, sometimes what you observe, that this particular curve never gets actually flattened, never gets saturated. Okay, and it does, so it gets somehow saturated, and then it becomes low slope. So high slope and then low slope, and it will continue forever. Okay, and this happens when the paramagnetic component, say for example, you are working with basalt, and basalt has some 1 to 2% of maybe ferromagnetic minerals in terms of its oxides. Okay, say for example, in a basalt you have magnetite, hematite. These are ferromagnetic minerals. Okay, in normal temperature, in room temperature. Okay, and that is being reflected or manifested by this hysteresis curve. But then it also has some components of paramagnetic minerals. So that part will be reflected. So if the paramagnetic behavior starts to reflect, you actually find out that the saturation magnetization is never reached. It actually keeps on shooting up, and then you have to actually correct for the paramagnetic component to actually find out your MS. But the MS, MRS, HC, and HCR are 4 different parameters that you calculate from a um, from a hysteresis loop, and which we will use later on for our purposes. Okay? So now within that ferromagnetic community, if you like, like there, like you have isotopes, similarly within the ferromagnetic community, there are few more areas of magnetization. One is called antiferromagnetic or anti-ferromagnetic. where after saturation, yeah, this is after saturation, huh? So when you subject it to the H to H, and then after it reaches saturation, what we find that the adjacent magnetic moments are equal and oppositely directed. Okay? And that's really, I mean, it has a very high susceptibility, you know, but then the net susceptibility, the net magnetization becomes zero because each other cancels each other, right? Then there is something called spin centered antiferromagnetism. So this is what this is, antiferromagnetic, but then slightly different looking. Okay? And what happens there is the magnetic moments, they are not essentially parallel to each other. Okay? Looks something like this. And then there is another called ferrimagnetism. Ferrimagnetic material. And this is when it reaches saturation. What we observe here are oppositely directed magnetic moments, but one moment, one set of moment is actually, higher in magnitude than the other. You can see the green one is stronger than the red one, so there is a net magnetic moment present. But for antiferromagnetic and spin-centered antiferromagnetic, you don't find any net magnetic moment. Okay, unless there is actually, there is something called, now if there is a defect in these systems, okay, and when there is a defect, what it creates, let me just find the term for you. Yeah, parasitic ferromagnetism. Parasitic ferromagnetism. So there is a defect. So that means this alignment is not perfect, and that can essentially result to some net magnetic moment to antiferromagnetic and spin-centered antiferromagnetic material. And in most of the cases, there are some defects. Okay, good. Now, so let's see now if you have any question. High reading sample magnetometer. That's right. Thank you, Shivangi. I forgot about the sample. Yeah. Okay. Any question that you might have so far?
Sir,
Yes, Vipul, please.
sir, is there any boundary for K from where we can define that this is paramagnetic and this is ferromagnetic?
I mean, boundary with respect to temperature, you mean?
Disrespect to value, because for positive K we are defining para and ferro both.
Oh,
So
yeah,
is
yeah,
there any
yeah,
boundary?
yeah, 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 yeah. Of course. So the mean susceptibility has to be more than 10 to the power minus 2 SI unit, if I remember it correctly. Uh, 10 to the power minus 2 SI unit. Yeah. Yeah, there is a boundary.
Okay,
Yeah.
sir.
And that is dependent on the mean susceptibility. Yeah. 10 to the power minus 2 SI unit, or let me take the number for you. Okay. I will write a WhatsApp message for you. Okay. It's either 10 to the power
Okay,
minus 2 or 10 to the power minus 3 SI unit. I just exactly don't remember that number. But I
okay,
will.
sir. I will check on internet.
Yeah, you can check it on internet as well. It's very easy to
Okay,
find
sir.
out. Okay?
Thank you.
Excuse me, sir.
Yeah, yes. Tell me.
So, like, I had a doubt.
Yeah.
When we were talking about magnetism,
Mhm.
can we say that the magnetism of a particular rock and or a mineral depends on the temperature and pressure variance?
Not so much pressure, but temperature. Yes.
Okay, so like I had a doubt. So if I'm talking about basalt, okay,
Right.
and if I'm taking it in, if what will be the magnetism difference when I'm considering the magnetism when in the lab or when it is in the crust? Like, will there be any difference in the magnetism properties of the basaltic rock?
No, I mean if it is very much present in the okay. I mean hold that thought, because we have to actually. So you have to look at, so basalt might have different minerals into it, right? So it will have pyroxene, it will have plagioclase, it will have hematite, it will have magnetite. Okay, and then all these minerals will behave differently with respect to temperature. Right? Say, for example, if I give you an example, and we will talk about it in a moment. Say, for example, if I give you hematite, okay, if the temperature is minus 23 degrees centigrade and below, it acts as an antiferromagnetic material. From minus 23 to 675 degrees centigrade, it acts as a ferromagnetic material. Okay, but not very strong ferromagnetic, but ferromagnetic. Okay, if it is more than 675 degrees centigrade, then it acts as a paramagnetic material. Okay,
So,
so that
sir,
is the, sorry.
yeah. So these negative temperatures are lab generated temperatures where we test the.
Yes, absolutely, absolutely.
Yeah.
So I'm just giving you a scenario. So this is the whole scenario for hematite, right?
So like when we are talking about when we are generalizing the magnetic property of that particular rock or a mineral, like, so what temperature are we using?
Okay, so now you have a certain set of temperature range for magnetite as well. Okay, similarly you have it for pyroxene. Similarly you have it for plagioclase. Okay, so let us say these four minerals we have. Now, the good thing about good thing about the ferromagnetic minerals, if they're present in 1 or 2%, that dominates over paramagnetic and diamagnetic effect. So, say for example, in room temperature, in a rock, I have pyroxene and I have plagioclase, and then I have magnetite. Okay, let's say pyroxene and plagioclase both are paramagnetic. Okay, for the sake of argument, let us say at room temperature. Okay, and that is the dominant constituent of that rock. Okay, but that is like 95%. I have pyroxene and plagioclase. So the rock primarily should be paramagnetic, because they are its major primary constituents are paramagnetic. But then it has 2 to 3% magnetite. So that will dominate over your pyroxene and plagioclase, and the whole rock will behave as a ferromagnetic substance. Okay, because they are extremely strong susceptibility dominant. I mean, they dominate the bulk susceptibility of a rock in a very large way. So yes, so if I look at a basalt, naturally occurring basalt, it will behave as a ferromagnetic material because of its presence, because of the presence of magnetite and hematite in its, so primarily magnetite in its uh, in its mineral structure. Okay, because although uh, they are not dominant in the minerals. Okay, but then they are not dominant minerals, but then having them 1 or 2% or 5% is more than enough to make the whole rock ferromagnetic. Is that clear to you, Yash? Is that what you have asked?
Yes, sir. Yep.
Is it clear? The answer is clear to you?
Yeah, yeah, yeah.
Okay, so that the ferromagnetic mineral will dominate. But if it is not there, okay, if it is, say, for example, in micro percentage, right, then perhaps it will behave as a paramagnetic mineral, paramagnetic rock. But then in basalt, you don't, I mean, hardly you find that it is devoid of any magnetite or hematite. Okay? So in that case, it behaves as a ferromagnetic rock. But now, if you take quartzite primarily contains quartz, right? So it will behave as a diamagnetic rock if it doesn't have any ferromagnetic component into it.
Yes,
I
thank you,
hope
sir.
I could answer the question. Yeah, Adil, go ahead.
Yes, let's say collected some rock samples and
Yeah,
I brought it in the lab.
yeah.
So, is it possible that the magnetization of the rock changes due to the Earth's external, means due to the Earth's magnetic field?
Okay.
In
So yeah, so that's a very good question. So that what we will discuss as well. So there are few things. One is what we call as the NRM, natural remanent magnetization. Okay. So natural remanent magnetization is, suppose you and we will talk about it in greater detail, but as you have asked the question. So now if you take out a rock, just you go to the field anywhere, for example, just by the side of our campus, you take out a piece of basalt, okay, and you measure its magnetic susceptibility. Okay, it's the NRM, natural remanent magnetization. Then you can actually take it to the laboratory and take it through some demagnetization process. Okay, and when you take it through the demagnetization process, what you will do, you will essentially decouple primary magnetization from secondary magnetization or induced magnetization. Now, what is primary magnetization? Primary magnetization is the magnetization that it occurred during the formation of the rock. Okay? For example, when to form that basalt, it was getting quenched from a lava and it was actually replicating the Earth's magnetic field of that time. Right? So that is my primary magnetization. Now that rock was formed 65 million years ago, right? And then it stays, I mean, it continues its journey for 65 million years. And meanwhile, the Earth's magnetic field has changed several times, right? So those changing magnetic field will actually and induce magnetization over the primary magnetization. And they are called secondary magnetization. Okay. So in the lab, we have processes by which you can filter out those secondary magnetization and you can you can find out your primary magnetization. Okay. So NRM, natural remanent magnetization, is the magnetization that you just take a piece of rock and you measure, and then you can essentially subdivide that into two categories. Of course, one is primary, which is nothing but when it formed, the magnetization that it acquired when it formed. Okay, and then it goes through stages of induced magnetization, and you can actually filter them out. Is that clear? And that is what we call secondary magnetization. Is that clear, Adil? Is that what you asked? Okay, excellent. I'm glad I could answer. Anything else? Chalo, chalo, pucho, ask. Because we don't have anything to, I don't want to start anything right now. Then it will be hampered. So let's just discuss for next 5 minutes about your doubts. Saima, do you have any question? Okay, excellent. Yadav, Krishna Yadav, do you have any question? Why the number of students very low today? 25, 26 only. What happened? Okay, Krishna doesn't have any question either. Babita, do you have any question? Ashish, Anand, Ashwin, Suhail? No. Okay. If I don't find many questions, then I am a little bit concerned. Am I able to solve your? I mean, am I able to communicate what I want to communicate, or it's you are not finding it interesting at all to ask questions? What is going on, guys? Can someone tell me? Rahul, just unmute, please.
Yes, sir, it's fine.
You are. Is it? Are you understanding things, or it's going somewhere else?
No, sir, it's fine. It's clear.
Okay, okay, very good. All right. If you don't have any further questions, then I will stop it here, and I will see you then on Wednesday. Thank you.